let's just keep cruising because there's so many moons. I am going to attempt to use this iPad today, which is only sort of working, but hopefully I won't have to be hunched over this desk so much. So yeah, there they are, by the way. This is what they look like if you get out your binoculars. I really hope. Has anybody done it since we've started talking about this? Do it. It's really cool. Yeah, guys, these are some of the only visible moons that you'll be able to see. And also, we're moving past Jupiter, so it's not going to get easier to see. Again, we're going to keep going through the moons. We'll hopefully talk about the rings of Saturn and the moons today, and eventually we'll get to the ice giants and Neptune. Or sorry, the ice giants and the trans-Neptunian objects, which include Pluto, who no longer is special enough to be a planet. But today, let's start with Ganymede. So, Casey mentioned Ganymede. Ganymede is enormous. So, it's actually the largest and most massive moon in the whole solar system. It's technically the 9th largest object, including our sun. And it's about 25% bigger than Mercury. So this is a really big body. And it also seems to have a metallic core, which is interesting because this magnetic core must be in some way different than the magnetic core, it has a metallic core, and the metallic core seems to be somehow different in that it may have fluid layers that allow for convection. And since it's covered in ice, it's hard to tell exactly what the tectonic situation is or how that convection is unfolding. But we'll explore that a bit. So Ganymede is named after this Trojan prince that was desired by Zeus. We talked about this very briefly last time. And we kind of looked at some of this a bit before. The Chinese were actually the first to really have detected this moon and talked about it. There's some debate as to whether they were correct about that, but for whatever reason, Galileo gets the credit, perhaps because the West didn't know much about China until very recently. So there we are. And there it is. So it's the last one in the orbital resonance situation. Of course, we'll talk about Callisto, and Callisto seems like it is coming into resonance, which will be interesting. There's some thought that this resonant pattern is very recently established, which has kind of evened out the eccentricity of Ganymede. Again, we're trying to claw at reasons why its internals are in motion enough to generate the heat necessary for a magnetic field, because it's actually got a really stabilized orbit that doesn't seem like it should be providing the tidal heating that we would expect otherwise. So, some of the best ideas for that are that things have changed very recently and that it's snapped into this resonance in a way that's stabilized it rather recently, like I think in the last a million years or so. And we'll talk about that. I guess several hundred million years ago, I'm reading now. So it's a strange one. And, it's it may have a history that it may have joined the party recently is another idea. But again, we haven't visited these places. It's very difficult to make any definite claims about it. All right. So it looks a lot like the moon. It has these dark patches, these white patches. It's got these enormous splatters all over it. It seems like it's got some different molecules other than typical, like different non-water molecules in its ice, like carbon dioxide, sulfur dioxide, a bunch of different organic compounds, which I think is quite interesting. The idea that organic compounds wouldn't be signals of life is somewhat modern idea. I think that folks thought that when we first started going out and exploring these worlds, that if we saw organic compounds, it would mean there was life for sure. And that's obviously no longer thought to be the case, and it's really changed our idea of geology here on Earth too, because like I said before, we don't really refer to hydrocarbons on Earth as fossil fuels anymore like we used to back in the 80s and 90s when I was growing up. We understand that they are naturally occurring. So there's quite a bit of organic compounds, and this makes it very tricky to sort out whether these compounds are occurring through natural means or not. And it makes it even more difficult because we can't get down to the rock water interface on these planets. Let's see here. So one thing that we do know is that it has this really interesting grooved terrain on it. And this is something of an unsolved mystery in planetary sciences. Because normally when we see these grooved things, we think about this tidal dissipation mechanism. And again, there doesn't seem to be enough eccentricity and sloshing going on to have produced these, which really, again, suggests that something different happened in the past. There's this idea that there may have been this actual expansion of Ganymede, something like as it cooled, which is interesting. That may have caused some of these grooves. There's thought to be some radiogenic heating, so some decay of elements that lead to it, but it doesn't seem like they're enough to cause, well, the melting of the interior that would lead to the magnetic field. What about let's take a look at the interior structure a bit. So actually, the interior structure, because mainly a lot of this is speculation based on the presence of the magnetic field, but we think that it's actually not too different than our own world. We think that there's this crusty, icy crust, rocky, crusty ice, dirty ice, I guess is the best way to think about it, on the outside, and that there's quite an enormous saltwater ocean. Again, these are based on density estimates. And then we have, something that looks a lot like Earth, a nickel iron core, some sort of transition zone there that's capable of sustaining those convection eddies that are necessary for the magnetic field. Another layer of ice above that, and then this salty ocean, which is, of course, perhaps really important. And actually, the thought is that the interface between the melted core, the liquid part of it, it's very hot, and the water seems, in most origins of life theories depend upon, especially when they're all basically concerning the Earth originally. Most of those theories depend on a hot interface between the ocean and the molten inner core mantle region. And it's thought that this, there's two thoughts. Maybe there is this interface, and maybe there isn't. Maybe it's actually frozen down to that because there's a pressure-based ice that's in the way, which is fascinating. All right. Talked a bit about this. This is its magnetic field. And because of this magnetic field, it does have these interesting auroras that are present. There's actually a very thin oxygen atmosphere, which is also promising. Although, again, this is really updating our view of oxygen on our own planet. We have this thought that all of the oxygen on Earth, the molecular oxygen in the atmosphere, appeared suddenly, and there's reason to believe that it did explode quite a bit when plants arrived on the scene, or moreover, algae, single-celled plants, I guess plant-like single-celled organisms that were able to photosynthesize. But it does appear that molecular oxygen can be produced in other means. And so that's really interesting when you think about what may have happened on early Earth as well. And in general, I think it's really interesting to look at the similarity between some of these bodies and early Earth. I think that the more that we study these different moons, the more that we'll actually update our understanding of what early Earth looked like. Because that picture has been changing rapidly. And, last time we talked about the process of these mini Neptunes evolving in other solar systems that we see out there and turning into these super Earths, which is a bit of a misnomer because they're not necessarily that much bigger than Earth. But there's this evolutionary process, and I think that the moons can, in some sense, mirror what some of those stages in our own planet's development were. And I think that might be the most interesting thing about all of them is none of them are exactly right. And of course, most scientists believe the moons were forming more or less in place, except for the ones that are rotating very strangely, especially around Saturn. We'll talk about that. So some of them may have been captured, but in general, they're thought to have evolved at the same time as the planets. And I think that can teach us a lot about what our early planet looked like and the conditions we should expect for the evolution of life, which is, of course, the biggest problem, I think, in all of science is how do you get life from things that aren't alive? And it's not an easy question. People are still working very hard to synthesize life from nothing on Earth, and nobody's really close to that. So, yeah, oxygen-rich atmosphere. There's some ozone that's been detected, and in general, it looks in some ways like we could imagine a very early Earth atmosphere, minus the water. It's very cold there, of course. We're actually going to go back. There's a mission under construction right now, which is called JUICE, which stands for Jupiter Icy Moon Explorer. And that's going to be pretty cool. So they're going to launch that in August of next year. And the plan is to orbit and then crash into Ganymede and send back some measurements. So look forward to that next year. I guess we're not going to crash into it until quite a bit later. It takes a while to get there. Yeah. So I guess they'll do a flyby. They're going to launch it in 2023. And they're going to do their first flyby in 31. They're going to crash it in 34. So go back to sleep for a while on that one.
Well, best things come to those who wait.
Yeah. I mean, these things are extraordinarily far away. It's hard to, if you can go back to our solar system tour at the beginning, it's hard to comprehend just how big this place is.
I know. I saw a video of someone was testing out whether light speed travel would actually hit anything. Like the hour he tried it, hit nothing.
Yeah, it's very empty for the most part. Although there are, we are crashing into things all the time. I saw a shooting star last night, which was pretty cool. And of course, that poor gentleman had his house blown up the other day in California by one of these things. So, it's not completely empty. What's that? Yeah, hopefully. I don't know. I mean, I didn't follow up. Was it covered by insurance? I hope he had some sort of home insurance on that. Jeez.
I'd just be more amazed on media.
It would be kind of incredible, yeah. I hope he got to keep it, right?
Constantly talk about that.
That's pretty much going to be your central story from here on out. Okay, so let's move on. Callisto. Callisto is the furthest one out, and Callisto is a really old-looking body, really, really old. In fact, it has so many craters that the craters are pasted over top of craters. So we haven't been to any of these places, and of course, that makes dating them, like doing the radiometric dating, impossible. Usually, when people are trying to date bodies they haven't been to, they look at the craters. This is what we did with the moon before we went there. That's impossible with Callisto because there's craters over top of craters over top of craters. And this has led people to believe that the thing is as old as anything else in the solar system. So whether it was scooped up from forming at some other place and then grabbed up by Jupiter, or whether it was formed at the same time is a bit difficult to say, particularly because Jupiter itself has no rocky surface. There's no way to date that thing itself. And again, we're stuck with the idea that, it's as old as anything else. The oldest dates that we can put on rocks here, last time they were molten was 4.5 billion years ago in this solar system. And so, Callisto is at least that old. It may be much, much older. In fact, I personally suspect it is very, very old. Very old. So, what else can we say about it? It's about the same size as Mercury. It's not quite in orbital resonance, like I said, yet. Although it does seem like it's changing, and it should be into resonance with these others very soon. I think it'll be a 1 to 8 eventually, and with the inner moon, Io. Let's see, what else can we say about it? There it is. I got pulled out your size comparison figure. You can see it next to our moon. It's bigger. What about its interior? So we make some density estimates based on its interior. And hold on one second. It doesn't seem to have this same iron core, which is interesting. And I think that is in some part based on the fact that it doesn't have a magnetic field, because what's interesting is that its iron to silicon ratio isn't outside of the bounds of the last moon we talked about, which did have an iron core. So compositionally, it doesn't seem to be that different, which is very strange. But like I said, it looks much older. And so perhaps that it's cooled. It's definitely beyond the reaches of the tidal effects that we would expect, right? Io very close, feeling a lot of that gravity from Jupiter. And gravity is a funny force because it falls off very, very quickly once you get away from a body. This is very obvious for astronauts who are going out into space. You don't have to go that far outside of the Earth to feel this weightlessness, right? And so this guy is quite a ways away. I don't have a picture of its orbit in here, but it's much further away than Io. Much, much, much further. So we think that it does have this subsurface ocean. If it is water, it's probably got some sort of naturally occurring antifreeze in it, because it would just be too cold out there. And we don't have this convection. We don't have this internal heating. We don't have this tidal heating. So if there is any kind of an ocean, it's got ammonia in it or something that's keeping it liquid. But again, no reason to really suspect that is the case. All right. There's a bunch of these impact craters. I mean, these impact craters are crazy, actually. So this one that you can see here, so you see these rings around it? Can you guys see that? There seems to be an impact with all these rings. This indicates that it was hit by something huge, like somewhere on the order of 100 kilometers. So 10 times as big as the Chicxulub impact crater that took out the dinosaurs. Something massive, right? And again, what would this do? Well, it's going to resurface the entire planet. It's going to reset all of your clocks. So again, we don't have much hope of going there and doing some radiometric dating, because the radiometric dating is going to tell us when this happened, right? It's not going to necessarily tell us when the planet was formed, which is a bit obnoxious. And I don't know that we'll ever know how old this thing is. This idea that planets can be captured up and that they might trade solar systems and things like this are quickly moving from science fiction to the hypothetical stage. The real trick is understanding how fast these orbital resonances can stabilize orbits. So generally speaking, the reason that we thought all of the planets and moons formed exactly where they were is because their orbits are phenomenally stabilized. But this is tricky because every single planet pulls on every other planet and body, and the way that these resonances appear, they'll tug on each other at the exact same moment each time. They can lead to quite a bit of stability really quickly. Like I said, Callisto is very quickly cruising into a resonance with the rest of the moons. So we don't know. And then there's a lot of speculation about perhaps the terraforming of this sky, bringing it back to life. What would that look like? It's thought that if there are vents, if there is that subsurface ocean, if there are vents, we might see some sort of microbial life down there. The main problem is not that there isn't the ingredients necessarily for life. The problem is, where do they get the energy? Where's the heat? Where's the any chemical reaction is essentially sped up by the application of heat. And otherwise, things might progress too slowly for life to have ever originated there in the time that it's been in the place that it's at. So I think a really good way to think about heat is it's very similar to time in chemistry. You can either wait a long time for something to happen, like a really long time, or you can apply some heat. It's essentially, we understand heat is a kind of motion, really. And so it makes sense that if you heat something up, you make it move quicker, things are going to happen faster. So that's really the main hurdle with imagining that life could even be there in the first place. People are particularly interested in it, though, as a potential space station and so forth, because it's outside of that radiation belt for Jupiter, which makes it a bit safer. Again, Jupiter has this really nasty radiation belt, which is going to make hanging out there next to impossible, and it's going to make it very difficult even for probes to get signals back to us and things like that. So folks are very interested in it. And there's some whispers at NASA of making a crewed mission, manned mission, womaned mission, manned mission, I don't know, crewed mission. Crude sounds like crude, like it's poorly done or something. Okay, we shouldn't expect anything about that until the 2040s, though. Cool. So those are the Jupiter moons. I wish we had more time. There's so many different intricacies of them. But let's check out Saturn for a moment. And before we really get into the moons of Saturn, it makes sense to talk about the rings, because that's obviously the most impressive and awesome feature of Saturn. And these things are just completely beautiful. So in some sense, there's not a lot to say about them in terms of our scientific knowledge, although we have taken some beautiful pictures of them, and we have a few ideas about their formation, which have evolved over the years, and we'll talk about them. But a lot of what I want to do is just examine the different rings and see, and because I think this is important. I think it's important because all of the gas planets and the ice planets have ring systems. So it seems reasonable that the ring structure is important in the evolution of these bodies in general. In fact, it's thought that these rings are going to be gone in a few million years because they're changing so fast. In fact, we've seen some changes happen in the short time that we've been out there, and we just had this we had a very sophisticated probe out there recently. Many of you saw some of those pictures in the news and so forth. And I think that when we think about the formation and destruction of moons, we would expect something like this in the past for Jupiter, which we just got done talking about. Its ring system was probably more developed at the time initially, and moons coalesced perhaps out of that. Moons crashed into each other and created rings, and that's one of the main theories for Saturn's rings, are that it is debris from leftover moon systems. Of course, it still seems to be accreting moons. There's moons embedded all throughout these rings, lots of moons. And we'll examine a couple of favorites and look at some of the little in-progress moons as well. So there's no real consensus though about their formation. I do think that the best thing we can do is think that it is a point in the stage of the development of all of these different moon systems. They're punctuated by these gaps, which is just these places where the particle density is extremely low. And the gaps can be explained both by the clearing mechanism of moons dragging out, dragging regions clean, but there's also orbital resonances established with each one of these clusters of particles that are going around, and they'll pull each other towards one another and kind of open up the gaps, right, as they get into resonance with one another. So two different mechanisms perhaps at play there. And then there's actually a whole other ring structure. This is kind of difficult to see. That little dot at the center of this ring, which is called the Phoebe ring, is Saturn. So there's a picture of Saturn there, but it's actually blown up. That little dot right there at the center is Saturn. So there's this huge ring structure very far out, and this one surrounds Phoebe, which is a moon, and it's thought that actually it is debris that's being constantly blown off of Phoebe as well. So, the fact that these rings seem to be still forming and still coming apart and still dissipating, it's very much a work in progress on both ends, coming apart, forming. There's new rings being made, there's old rings disappearing, and it's really something to just keep an eye on. So when it comes to looking at Saturn from Earth, it's a highly variable situation. So Saturn is tilted much like the Earth, a little bit steeper, 26.7 degrees, and we'll make a pass through that plane where we can get a good shot of it every 13 to 15 years, which is interesting, and that's only half of a Saturn year. And so the most recent one was in 95. And then we'll see this again coming up in 2025. And so it's a highly variable body to observe from Earth. You get a pretty decent ring picture right now as we approach that. We're actually close enough that I've actually been out this summer and seen some pretty good. You can actually see it, I think, with binoculars too, if you want to try this out. Saturn is visible right now. We have a little telescope too. Maybe that's better. Has anybody seen the rings with their own eyes? Yeah, pretty cool, huh? This year?
I think a few years ago we have a big telescope at my house, so we like to look outside.
Nice. Yeah, I saw it very, very well this summer, but I think it'll be even better in a couple of years. So, yeah, this is one of those things like Jupiter's moons, Saturn's rings. These are a few things that you can actually pull off with really low tech. Highly recommend it. And it's going around very slowly, so your chance won't come again for a while. I think you'll, let's see, after 2025, you're going to have to wait till 2038. 2038, 2039. So get out there while you still can. All right, so these rings are just so beautiful. There's a number of different gaps which house different moons, and they all have they're all quite different and characterized. These moons, actually, for the most part, will tend to look like little asteroids. This isn't a great view of it. Let's see here. This is a little bit better. The rings actually seem to have some sort of very rarefied, thin atmosphere of their own, which is fascinating because if these do indicate a moment in the evolution of moon systems, we can start to imagine where this primordial oxygen atmosphere came from. And we've seen these oxygen atmospheres on some of the moons of Jupiter. And so we can imagine that a similar situation may have occurred in the past on Jupiter as well. There's molecular oxygen out there, which seems to happen when the sun's radiation interacts with the ice crystals right? I don't know if I should have mentioned it, but these rings are primarily dust and ice, and a lot of that is water ice, interestingly enough. There's also a fair amount of other water-based radicals that would be appearing in addition to oxygen, molecular oxygen. You get molecular hydrogen, but you also get hydroxide ions and things that are more reactive. Enceladus, whom we'll get to in just a moment, has these geysers too. This is one of the more exciting moons in the solar system. We have actually tasted them. We've been there with our probes. And so it's thought that actually the production of some of these rings, atmospheric particles, come from those geysers themselves, which is quite interesting. People think that the rings are actually a relatively recent formation. And there's no dating on those in terms of radiometrics or anything like that, but it's thought that they may have formed within the last 100 million years, which is, I'm always absolutely dumbstruck by how fast these bodies are thought to have formed. And I don't know if that's a result of the fact that we can model them as being formed so fast, or if it's an artifact of the fact that we're trying to squeeze everything into these tiny timelines, or if it's truly the case that they are very young. Maybe so. The idea is that these rings are dissipating quite quickly as well. So they are being produced in some sense, but they're also losing material. And they're losing material so fast that we think they're going to be gone in 300 million years or so. And if they're going to be gone in 300 million years or so, well, they must have been bigger in the past, and therefore the timeline for their formation is even shorter. And so we think that they must be a relatively recent phenomenon. There's been some interesting studies in the news lately about the formation of these bodies. And of course, these theories are often at this point different computer simulations of how you can take one body and make so many, and so on and so forth. And really, the establishment of that moon hypothesis was almost really the first one. As soon as people started thinking about how these things formed, I think this was as far back as the 1800s, Edouard Roche in the 19th century established that, well, the best way to make one of these would be to crash a moon into another moon. And so some version of that theory has persisted up to the day. And there's been a number of different evolutions of that idea and ironing out the particularities of that. But the idea has essentially remained the same. And this would also help us to explain the youth of these rings, because they could have been produced long after the body itself was produced. And maybe this helps us understand the short timetables also. There's a competing theory that that instead of the result of some disaster, that it was actually the capturing of micrometeoroids from the initial moments. Again, this is troubled by the dissipation kinetics, because if that were the case, we would have to have had an enormous ring structure in the first place, which isn't out of the question. It's just that we don't see anything like that. We don't see anything like that when we look out at other solar systems yet either. So, mysteries. Again, the further we get away from our own Earth, the more difficult it is to make definite statements about these. Ooh, this is just a breathtaking image. You can see these rings are evolving in real time. So this is, what body is this? This is Daphnis, which is one of the moons that lives in the Keeler Gap. All these gaps have names. The scientists, of course, name them after themselves. But you can see that as this thing skips and twirls through the rings, it's actually kicking up new structures behind it, and it's going to compactify those regions, and this will lead to more more resonance between those different particle systems, and eventually you could maybe even get the production of another body as a result of that. I think these little turbulence effects are really the way to think about how we cross that pebble to boulder boundary as well when we're talking about the formation of bodies in the solar system, because it's not sufficient. A lot of these things aren't sufficient mass for them to collapse upon themselves. You need some other process. And this is a really cool example of the turbulence that you would expect in a newly forming system. I think there's some analogies to be made about how the star system formed in the first place, because ultimately, what is the circumstellar disk if not a very complicated and robust ring structure, right? So in some sense, this is like a little toy version of perhaps the early solar system as well. And we can think about these turbulent processes playing out that way as well, which is cool, because we can see them up close, and they're quite beautiful. Here's another version. You can really see these grooves being cut into this ring structure. This is Prometheus, another little baby moon. It's in the F ring. Just stare at that for a second. Okay, so there's many, many moons for Saturn. So technically 83 of them that aren't even part of the ring structure, and then many, many, many more that are those little asteroidy looking tiny little moons that are embedded in the ring structure. So are those moons that are in orbit, were they formed within the ring structure and cast out in some way? Perhaps. There does seem to be an interesting pattern with Saturn's moons. Let me see if I have a picture of this. Well, we'll get to it in a minute. The moons, some of the moons orbit the wrong direction, which is very, very interesting. Whenever we see something orbiting retrograde, that is opposite the rings, opposite the rotation of the planet, we have to start thinking about a capture mechanism so that these things were formed somewhere else and then swooped up. And there's a few of those, which makes it really interesting because it brings to the imagination to the point where the body was traveling and encountered a region or disturbance. There was some bigger event that occurred that led to all of these orbiting. And I apologize, I think I have a picture of these different orbits in a minute. And you'll see that they cluster together, and the retrograde moons kind of cluster in one plane, and the prograde, the normal moons, cluster with the rings and so forth. So two different events there must be playing a role. And these are the bigger ones. These are the major moons. I think the two that we'll have time to really talk about, the two that your textbook focuses on, are Titan and Enceladus, and we will get into those. Again, this is a nice animation, a bit out of order from what we were talking about with the explosion of a moon, a shattering of it, I guess, and the production of these rings. So, speaking about the moons, one thing that's really interesting is that Titan seems to contain almost all of the material of all of the moons compared to all of the moons. I think that it's in the upper 90%. Let's see, 96% of the mass of all of the orbiting bodies are contained within Titan. So that makes it a very intriguing one to study. And we'll do Titan in depth in just a second. Okay, here's the orbits. This isn't showing up very great. I'm sorry. Yeah, sorry, we can't even read those. I'll do better next time. So Titan is incredible. It's mostly made out of nitrogen, so it's an atmosphere that's not so incredibly different than our own, which is interesting, and it has a little bit of methane. And there's some weather and convection clouds, especially over the South Pole, and the presence of some interesting hydrocarbons in the atmosphere as well. And again, when we see hydrocarbons, we think, well, maybe something is alive that's producing these, maybe not. It's difficult to say. Titan also has some really interesting surface features we'll get to. There's these hydrocarbon lakes on it, which are quite fascinating, and it's really led a lot of scientists to hypothesize that there could be life forms that use those hydrocarbons as a solvent instead of water. Although I think it's maybe a bit of a long shot, because water seems like a irreplaceable chemical when it comes to life. It's, we talked about water a few weeks ago, but it's hard to beat. There's nothing like it. What else can we say? So it's the second largest satellite in the solar system, Titan. And it's the only one that has a really dense atmosphere, which is fascinating. And it's also the only body, other than our own planet, that has stable liquid on the surface. Now, it's not water, but it is still lakes, and we don't see that anywhere else, which is quite fascinating. We think that, we'll get to the composition in a second. Huygens, we've talked about Huygens a few times. Huygens was the gentleman who actually first deduced that Saturn had rings, and Huygens also noted Titan and is considered to have discovered it. He's a real character. I think a very dandy-looking chap, but he's contributed. It's hard to think of anybody else in the history of science who's done more than Huygens. He gave us the wave theory of light for the most part that we have today. He worked a lot in mechanics and elasticity, and just an amazing guy, actually. Of course, back then, it's really funny because scientists weren't. There was no professional science, right? You couldn't be a scientist when you grew up, and so, of course, almost all of the people that did science in the Enlightenment era, where they were stupidly rich to begin with, and they had all of this spare time, right? They didn't have to work, and so they would sit around and tinker with this. And the man built his own telescopes and so forth, and pretty cool, but it's highly unrealistic in today's age. It's always fascinating to me that when you read about these scientists from 300, 400, 500 years ago, none of them are just like an astronomer or a biologist or something. They're all doing everything all at once. And I think this is a really tantalizing paradigm, because it seems like a lot of times today when we go into science, we get stuck in these really little areas, and the scientists don't have a lot of communication with people. So the biologists have a hard time talking. They don't go to the same conferences as the physicists or the astronomers, and so the cross-pollination of that is a huge issue right now, how to actually get people to work together on ideas, because, of course, the biologists have a lot to say probably about the production of different atmospheres and so forth, but not necessarily as much of the conversation as they would have been 400 years ago, because there was no specialization back then, which is interesting. Okay, so Titan, of course, comes from Greek mythology as well. This is this race of giants, which makes sense. It's an enormous moon. Oh, here we go. So Titan is this red one, Saturn being at the center, and the Phoebe ring being out there in the distance. It's relatively close, but it's not actually inside of the ring. It's quite a bit outside of the ring structure. It orbits once every 15 days or so, well, closer to 16 days. And just like most of the other moons that we see, one side of it is tethered to the planet. It's tidally locked, that's how it would be said. So one side of it is always facing away, and it experiences days and nights as a result. There she is next to our moon, a bit bigger. It's a little bit bigger than Mercury as well. And Voyager 1 was the first one to get out there and check it out. And before Voyager got out there, we thought that Ganymede was the biggest moon, but that turned out not to be the case. Let's see. This atmosphere is kind of interesting. So it's the only moon that we know of that has a really significant atmosphere, and you can see a picture of it there. I believe this is from the Cassini, Huygens spacecraft. Oh yeah, the spacecraft Cassini has the surname Huygens after Christian Huygens. You always hear it called Cassini. Huygens doesn't get mentioned. It's his spacecraft too. So it's an interesting atmosphere. It has a pressure that's not that's on par with our own atmospheric pressure. It's very hazy. There's a lot of organics and inorganic volatiles that obscure our view of the surface. And we've done some radar imaging, so we'll get to that in a second. But the atmosphere has all sorts of interesting molecules in it. Ethane, acetylene, propane, hydrogen cyanide, carbon dioxide, monoxide, all of the interesting things that we might expect to see associated with life. And it seems like when the sunlight hits that methane, it breaks it up in an interesting way that leads to that orangish smog, which obscures the surface. So because the question is why hasn't that atmosphere blown away, given the timetables associated with the formation of these things? And it actually, Saturn has an enormous magnetosphere, and it's thought that because Titan lies just inside the envelope of that the magnetosphere can shield it, and it's able to keep its atmosphere as a result of it. It's an interesting hypothesis. I don't know, though. I mean, Enceladus also, we'll deal with Enceladus in a moment. And Enceladus is, of course, shedding tons of material, and it doesn't seem like the magnetosphere is doing much to protect Enceladus. So we'll see. So much work to be done. Who's going to go out and be a NASA scientist and figure this stuff out? Somebody's got to do it. A lot of work. Job security. What else can we say? So one of the, they've seen the presence of these tholins, which are, generally were only associated with living organisms before, and we've seen some of these, I believe, on one of the other moons that we talked about in Jupiter. Certainly, these tholins are giving off a lot of the coloration that we see on Pluto, if we ever make it to Pluto. And so, there's all of these little tantalizing signs that something either lived there in the past, maybe still lives there. And it's going to be very interesting exploring those things, because one of the first things people are going to think if we find life there is that we accidentally brought it with us. And so how do you separate that out? What if the life actually looks very much like life on Earth? Would we be able to even tell the difference? There's like two different pathways. Usually evolution is treated as just this one pipeline, like things evolve, right? But what's interesting is that you can have things evolve from, say, a common ancestor, but you can also have things evolve because of a common environment. So if the niche is sufficiently similar between two different organisms, for instance, a good example would be bugs and birds, right? They both fly, but it's not like birds evolved from dragonflies or something like that, right? So they both evolve wings, and the wings aren't that different. They're different, fair enough. But the issue becomes when we go out into the solar system, if we do find life, will we be able to tell, okay, this thing has a genome that looks a lot like our bacteria. Well, did we bring our bacteria with it accidentally? Or did it just evolve that way because that's essentially what life would look like anywhere that you find it, because the pathways would converge on the environments because the environments are sufficiently similar to allow for life. And I think that's going to remain a huge hurdle. And I imagine if we do find anything alive, that's exactly where the discussion is going to turn to. How will we be able to separate out our life from their life? Of course, they could be radically different. Instead of finding bacteria that look like ours, maybe they're wildly different. But most people don't suspect that that's the case. So we'll see. These are some interesting infrared maps that are, these are spectrum maps that are showing some of the aromatic hydrocarbons that were found in the atmosphere. Propene, which is also thought to be associated with life forms. All right. It's very, very cold there, about minus 180 degrees Celsius, which means that there's very little water vapor present. It would be condensed down into ice for the most part. That atmosphere is so thick that very, very little light reaches the surface. And all of this methane does create some sort of a greenhouse effect, but certainly not significant enough to warm the place. So we have been able to do some radar imaging, that's what these images are from, of the surface, and get some terrain maps back about it. This is from the Cassini-Huygens project. And it seems like these features are volcanic for the most part. There's maybe some cryovolcanism, so water mixed with ammonia spewing out onto the surface, which is interesting, and it's produced something of an ice shell on the place, which seems very hard and doesn't seem like there's much geoactivity continuing at this point. It's also these streaky organic features, which is interesting, perhaps wind-blown particles or some sort of river-like entities. There's another picture of these. So I think the most striking feature that came back were these hydrocarbon lakes, which I mentioned. You can get a picture of them here. This is a polar view. I'm not sure what these darts are from. There's missing imagery. This is liquid methane, which is quite fascinating. And Hubble is actually able to image these things right now. And these are interesting mainly because they give us the chance to actually go there at some point in the future and check out these soups and see maybe there is a completely different pathway to life that we're not even imagining. But certainly life as we know it wouldn't be swimming around in these lakes. Yeah, more of that. Very beautiful. Again, more of these beautiful lakes. Let's keep going. Oh, this is kind of interesting. So they found these sort of dune-like features, which is quite fascinating, which indicates that there might be weather patterns similar to the ones that we have on Earth. Again, the atmospheric pressure is similar to Earth. So above, you have some sand dunes on Earth, and down below, we have these pictures from the surface of Titan. Let's see if I can bring this down a little bit. Shockingly similar looking, actually. Unlike our own sand dunes, though, these don't seem to be made up of the same sort of silicates, but they actually seem to be something like liquid methane rain that comes down and erodes the ice on the surface. So maybe a similar water pattern, but very different composition to what we have here on our planet. We did crash down into Titan, which is interesting. There was a little lander Huygens was this piggyback probe that was sent off of the Cassini and plopped down. And actually, I encourage you to go watch a video of this. It's quite fascinating seeing it come down and crash. But we essentially ended up with one picture as a result of that, which you're staring at right now. And though I don't personally see it, I'm told that this picture illustrates some sort of methane rivers in it. I don't see them myself, but somebody saw them. This probe was actually only able to send data for 90 minutes before something broke on it, which seems to be typical of a lot of these landers. Although it seems like we're planning to go back. So there's a mission, let's see. Well, nothing's actually planned for launch right now. So there's soliciting design concepts for another lander. It'll be interesting to see how that plan plays out in the future. But I think people more have their eyes on Enceladus, and we'll see why. Here's some thoughts of what its subsurface world would look like. Honestly, not so different than some of the other moons that we looked at. But of course, we're extrapolating to some degree. We don't know. We haven't been down inside of it. But from the density estimates, we do think that there might be a water ocean down there, which is perhaps cut off from the underlying mantle. It doesn't seem to be a lot of the upwelling and pluming and geothermal activity in general. So again, we don't think that, and there's no magnetic field, so we don't think that there's a warm layer down there, which honestly probably makes it a real long shot that we would find life there, because that interface between the magma and the water seems really important for the origins of life. Unless, of course, it happened at some point in the deep past. There have been, which is possible, there have been some really interesting complex molecules that have come back after these Cassini probes wandered around there. Some really complex carbon chains floating around in the upper atmosphere, which is giving people some hope. It's thought that this ammonia water solution up at the top would be passable to some extent, and so we might be able to get a look down there if we make the right probe. But in general, I would say not looking as promising as our next world, Enceladus. So, all right, we got 5-10 minutes left. Let's make it through Enceladus, and then we'll start with the ice giants next time, the moons of the ice giants. So Enceladus is the 6th largest moon of Saturn. It's only about 300 miles across in diameter, which makes it like a tenth the size of the one that we just looked at. Very cold. It's covered in this very fresh, clean ice, which is constantly being remodeled. And that makes us think that there's a degree of youth to this, or at least a degree of turnover. There's much more hope for something interesting in the subsurface ocean because of how fresh this place looks. There's something happening there. Enceladus is also named after a giant from Greek mythology, by the way. And one of the things, this was one of the first signs of these plumes, which are very exciting. We flew by there with the Voyager program back in 1980 and 1981, and then Cassini, of course, has done a lot of the follow-up. Now, Cassini was the one that really dug into these plumes and was able to taste them and make some actual direct observations of their content. It's a tiny little moon, so that's it compared to ours. It's also it's a bit closer than the last one we looked at. It's one of the big major inner satellites. So there's a different group of outer satellites. And it's in resonance with Dione, which is difficult to read. So it does 2 orbits for every one that Dione does. And this is thought to stabilize the eccentricity. Oh, one more thing to say about it. It's orbiting actually within a ring, technically, within the E ring of Saturn, which is the outermost major ring. And it's thought that that ring is predominantly composed of the material that's being blasted out and off of Enceladus. Which again, oh, here's a cool picture of it. So there it is. There's Enceladus making its ring, which is really cool. Again, I'm not sure why this is not magnetically protected. I'll have to get back to you on that if anyone knows. The interior, yes, the interior. This is a better picture. Okay, so owing to the fact that it doesn't have its own magnetic field, and it's based on density, we don't think that it has this nice, warm, molten inner core, which maybe it did in the past, again, but we're probably not going to see new life forms popping up there. So if there's anything, it's probably from the past. The material that's being shot out does appear to be particularly salty, which is interesting because the salts are quite useful in the construction of life forms. We think that ocean is quite a bit below the surface. So if we want to go visit it, we're going to have to find either some sort of in through one of those plume geysers, or we're going to have to drill really far. And the drilling seems preposterous because it's like 30 kilometers of ice. So either we're going to melt our way through, or we're going to find a way to get through the cracks that are already there. When we checked out those plumes, we found they were highly alkaline, which is interesting, very, very basic. And this could happen in a number of ways, but it's thought to have resulted through an interaction with some of the rocks that are down below, this process called serpentinization, which is interesting because we actually out here, what's the name of this wilderness? The Kalmiopsis, am I saying that right? Kalmiopsis. Full of serpentine rock also, which is thought to, it's very beautiful greenish rock, and it's thought to be the source of a lot of the chemistry that we see on Enceladus, a very similar process happening out there. And it must have happened at some point in the past here as well, since it's all over the place. There's also carbonate salts in those plumes, which is another biological precursor. The one thing that's interesting is that we have a difficult time explaining the heating of it, right? How there does maintain a liquid component to it. We think there's liquid because there's these geysers, but it doesn't seem like there should be this radiogenic heating that's pulling it off, and the tidal forces also don't seem to explain it. So this is a bit of a mystery. The power output from tidal heating alone doesn't even come close to the heat that we would need to maintain those oceans. So again, another huge mystery if anybody wants a job in the future to figure this out. I think that understanding the internal convective processes of all these moons, both the magnetism and how the heat is generated, is a huge final frontier in planetary sciences that is really poorly etched out. I think we'll look back in 100 years and feel like we knew next to nothing. So those are the moons of Saturn that we have time for. Those are the moons of Jupiter that we have time for. We will dig into Neptune and Uranus next time, Pluto, and then we'll move on to the icier tiny bodies after that, and We're getting very close to the end, my friends. So hope you are enjoying the tour of the solar system. And I hope you guys have a wonderful break. I hope you get recovered and rejuvenated.